Hi everyone, thanks for joining us today. We're the Essence CubeSat verification team, and we are excited to present to you the work we have done for the Essence CubeSat mission. This includes both thermal and structural verification testing of the current CubeSat design. This presentation will outline what this testing means, how it was conducted, what our final results showed, and possible future work to be completed. The Essence mission is a part of the Canadian CubeSat project funded by the Canadian Space Agency. The purpose of this project is to encourage post-secondary student involvement in a real space mission and to provide experience with planning, building, launching, and eventually operating their own CubeSat. This mission is run by the York University faculty and students, and its focus is to use the payload to monitor snow and ice coverings in northern Canada, as well as collect radiation measurements in orbit to understand its effects on the spacecraft. Prior to launch, the satellite must undergo a series of rigorous testing to ensure it will be able to survive its mission duration. The purpose of our project is to complete the thermal and structural testing for the CubeSat to ensure it's able to, first, survive the vibrational loads imposed on the surface of the CubeSat from the launch vehicle during the launch phase, and second, to be able to survive the temperature cycling when it reaches its orbit. The satellite will be in an orbit similar to the ISS and will therefore have an orbital period of about 100 minutes. During this time, the satellite will experience a drastic change in temperature as it moves from direct sunlight to eclipse, which can cause stress to the satellite structure and components. To determine if the current design is able to withstand these stresses, a finite element analysis must be completed.
To achieve our project objectives, there are a few steps we must take. The first step is simplification. This is where we simplify all model geometry. The next step is mesh. We define all material properties here and prepare our model for simulation. We then test our mesh and ensure that our FEM is optimized and simulation results are accurate. Simplification is the first step in our project. Simplification is necessary in order to reduce our simulation runtime and achieve results quickly. We keep all of the important components of the satellite and delete any small parts that are not needed for simulation. For simplification, the process is as follows. We take measurements of the part we are simplifying. We then delete any unwanted geometry. We replace the deleted geometry with simpler geometry, such as cube or prism. The image in the center shows the geometry after the small components are measured and replaced with larger geometry. For small parts of the satellite, we skip steps 1 and 3, as small parts do not need to be replaced.
To begin thermal analysis, we created meshes for important components of the CubeSat, such as rails, standoffs, solar arrays, PCB, and side plates. By meshing, we can split the complex geometry into finite number of elements to solve for the temperature of CubeSat at different time and place. Before we begin meshing, it is important to create three properties, namely material property, physical property, and thermo-optical property. By creating material property, we can define the density and important thermal properties such as thermal conductivity, which is the ability of a material to conduct heat, and another property called specific heat, which defines the heat required to raise the temperature of a body by 1 degree. Two main modes of heat transfer in space is through conduction and radiation. The amount of heat a body can absorb or emit due to radiation depends on the surface properties of the material, also known as thermo-optical properties. Finally, we have to define the physical property for different components, which determines the thickness of meshes. We have both 1D and 2D elements in our finite element model. The 1D mesh calculates the linear conductance of rails, standoffs, whereas 2D mesh has surface properties associated with them. The image on the right shows the 1D elements and the image on the left shows the 2D elements. Also for 2D elements, radiation on top is enabled for all parts. Finally, we connected the elements on different parts through mesh mating condition.
For the structural mesh, we use a combination of 3D and 2D meshes. All plates and 2D components with small thicknesses are defined as 2D meshes with element type C trier. All 3D objects with large geometry in all axes are defined as 3D meshes with element type C tetra. Material types are defined with mesh collectors, and the following materials were used. We used aluminum 6061 for the main structure and frame of the satellite. Stainless steel was used for the standoffs. FR4 was used for all PCBs and solar arrays. Polyamide was used for the battery and for the camera, or in this case, the mounting plate, as the camera was deleted from the structural FEM. For project testing, we conduct the following tests. Element normals. This is where we ensure all normals are facing the correct direction. We want all arrows to be pointing away from the interior of the satellite. Duplicate nodes. We check if any duplicate nodes exist. If they do, we merge them. Duplicate elements. We check if any duplicate elements exist. If they do, we delete them. Element quality. We run a test to check the quality of our elements. We want to minimize the number of failed elements. We can adjust the element quality by reducing the size of our elements. All tests are conducted for both thermal and structural meshes. The purpose of these tests is to optimize our mesh and ensure a more accurate result from our simulation.
To determine the thermal stress imposed to the surface of the satellite structure while in orbit, we needed to determine what temperatures the satellite would experience over time. Specifically, we needed to output what the extreme temperature values were, so its hottest and coldest points, to then determine what maximum stress they would impose on the satellite. To do this, we set up hot and cold case scenarios. The hot case modeled the satellite temperatures if deployed in direct sunlight, and the cold case modeled the satellite temperatures if deployed in eclipse. These scenarios were run over 10 orbits to output our final temperature results.
The cold case result shows us that temperature of CubeSat ranges from negative 87 degrees to 114 degrees Celsius. The maximum temperature is on the side facing the sun, since it receives high solar flux compared to other phases. As this side heats up, temperature flows to the colder surfaces and radiates away. The temperature generated on internal PCB are transferred to other parts through standoffs. The maximum temperature on the PCB is 20 degrees Celsius.
Once the temperature profile of the CubeSat was computed using finite element analysis, it could be mapped to a structural model to determine how these thermal loads induce stress, and if the stress is larger than the yield strength of the spacecraft material. As seen here, the average stress caused by the cold case temperatures was about 53 megapascals. The yield strength of aluminum 6061, which is the material of the chassis, fluctuates with temperature. At 100 degrees Celsius, its yield strength is about 260 megapascals, which is significantly larger than the average stress induced. As seen on the left-hand side, the maximum stress induced here is about 668 megapascals, which occurs at a welded part which has a very small mesh value. Because of this, the stress can be ignored as it is not entirely accurate to the actual model.
During the hot case scenario, the CubeSat spends maximum possible time under the sun. Due to this, the temperature is 15 degrees higher than the maximum temperature seen during cold case. Although this only affects the temperature on exterior faces, and the internal temperature on PCB remains the same compared to cold case scenario.
Similar to the cold case, once the temperatures were output for the hot case, they were mapped to the structural model of the CubeSat and the stress was output. As seen here, the average stress was smaller than the cold case at about 37 megapascals. As stated previously, the yield strength of aluminum at 100 degrees Celsius is about 260 megapascals. Therefore, the model will be able to survive the hot case thermal loads. However, as seen in the maximum stress figure to the right, the negative Z plate on the CubeSat has a significant amount of stress imposed to the surface. This was caused due to an improper thermocoupling to the plate, which caused a large decrease in temperature. Because of this, these stress values are not accurate to the true response of the model and can be ignored.
Similar to the thermal analysis, we want to first create a finite element model for the CubeSat. After we create the meshing and start the simulation, we then realize there's an issue with the part not being connected. As we can see from the simulation result from the figure on the left, the software will randomly select one part of the model to perform analysis instead of the whole model. This can be fixed by using welding to the model to attach all the parts into a whole, which will look like the model on the right. With that, we can now perform simulation on the CubeSat as a whole. For the structural analysis, we want to perform two types of analysis. The first is normal mode analysis, which will give us the natural frequency of the CubeSat. This is crucial as it will determine the frequency that will cause a large displacement. The next will be vibration analysis. This will give us the stress and deformation caused by any enforced motion on the CubeSat. With the output, we can compare it with the material yield strength and study if yielding will occur. After applying constraint on the CubeSat and running a normal mode analysis, we got the first time mode of the CubeSat. We only take the first time mode as the following node will not matter much in our analysis. The table on the left is the result we got. The first normal mode will start from 424 Hz, which is much larger than the 100 Hz requirement when launching the satellite. This means that the CubeSat will not have a large bending when launching. After the normal mode analysis has been done, we can then proceed to the vibration analysis. We apply an enforced motion at the corner of the CubeSat to simulate the vibration. Then, we run the analysis to look at the stress and displacement caused by those forces. Above show the result of the analysis. On the left, it shows the displacement analysis where the structure will experience around 8 mm of deformation and the maximum stress is only about 3 MPa at the corner of the PCB. The PCB is made out of FR4 and the yield strength is around 245 MPa. This means that our structure will have no permanent deformation from vibration and is good for our design.
For simplification, we needed to start sooner to optimize our schedule. This would give us more wiggle room for mesh and testing. Systems Toolkit Analysis. This part of the project was scrapped as the satellite design was too complex and the software had limitations that restricted us from obtaining results. This took a lot of time during the first semester that could have been used in other areas of our project. For mesh, the parts should have been meshed separately. During simulation and testing, it was hard to add parameters to individual parts that were meshed in groups. We had to go back and remesh parts in order to assign different component parameters. This wasted project time. For thermal, adding internal thermal loads increased the temperature due to absence of radiation on the bottom face of the side plates. On the other hand, enabling radiation significantly increased the simulation runtime to several days. Therefore, all thermal exchange between elements were completely discarded. Structural. For the first vibrational analysis, we encountered the issue of the satellite components separating during our test. We needed to add a connection between these components before running the simulation, so a lot of time was lost here as we thought the solution solver was the issue and not the mesh. Another issue was that the results file created for the secondary vibrational analysis was too large, and results could not be obtained. This issue was worked on over several days, and the problem was never resolved. Therefore, our secondary vibrational analysis failed. For the future, more research is required to obtain all material properties. This will ensure simulation accuracy and consistency, as we had to conduct our own material property research, which interfered with our simulation time and made all of our meshes inconsistent with one another. For thermal simulation, we need to add internal thermal loads. Although runtime will increase, this will ensure the most accurate results. For structural simulation, we need to run analysis in both the x and y-axis directions. We only obtained results in the z-axis direction to simulate the direction of the launch vehicle. We could also add more complex geometry for both simulations to ensure greater accuracy. However, this will increase the runtime as well.